Okay, let's talk about transition diagrams. So let's say we have a process and it's got 3 states, and we're just going to call them 0, 1, and 2. Okay, so we can depict this as a diagram that looks like this. And the nodes, one for each state, represent the system being in that state. So let's say, where are all of the possible transitions? So state 0 could go to state 1 or state 2. State 1 could go to state 2 or state 0. 2 could go to 0 or to 1, and any state could theoretically go back to itself. Because if a state doesn't change, if a system doesn't change within one transition, then it just goes back to itself. And then for each one of these arcs, each one of these transition lines, we're going to have some non-negative probability. So let's say, for example, that we have a state where, let's call 0 that it's sunny, 1 if it's cloudy, 2 if it's rainy. And let's just call this rainy or other. We're going to include partly cloudy and all the splitting hairs on here. If it's precipitating, it goes in here. Okay, so let's say that we know that the probability, if it's sunny today, the probability that it's cloudy tomorrow for wherever this happens to be is 0.3. And let's say that the probability that we have 2 sunny days in a row is 0.3. And let's say that the probability that if it's cloudy, that it's going to be sunny tomorrow is 0.4. So the probability if it's rainy that it's going to be sunny tomorrow is 0.2. And then let's say the probability if it is rainy, it's going to stay that way is 0.1. And the probability if it is cloudy that it's going to be rainy, let's call that 0.5. Okay, so I can put these into my transition diagram so I can see what's going on. So if I have 2 to 2, probability of 0.1, from 2 to 0, back here, 0.2, 1 to 0, 1 to 0, 0.4, 0 to 1, 0.3, 0 to 0 is 0.3, 1 to 2, 0.5. Now what about these other arcs? We don't have a 1 to 1, we have a 1 to 0. Yeah, okay. So what about all these other arcs? Now, for example, let's take state 0. So right now we have an arc coming up with a 0.3, 0.3. So since all of the arcs coming out of 0.1, they all have to sum up to 1 because you're going to go from 0 to some others or to some state in the next step. There's a 30% chance you're coming back to 0, a 30% chance you're going to state 1, and that leaves a 40% chance of going to state 2. If you're in state 1, we know there's a 40% chance of going to 0, 50% chance of going to 2, which only leaves 10% chance of being cloudy 2 days in a row. And down here, we've got a 10% chance of staying in state 2. We've got a 20% chance of it going to sunny, and so that leaves us with 70% chance of going to being cloudy. Okay, so that's your transition diagram. Now, it is possible to have a probability of 0 on any one of these transitions. So let's just say, for example, that this one, instead of being a 70% chance here, let's say that we don't know what the probability of staying cloudy is. And let's make this a 0.8 instead. Well, we've got 20% out of here, or 0.2 out of here, 0.8 out of here, and that leaves nothing for 0. Or for state 1, for P11. All right, I'm going to go back to the example I had a second ago. Okay, so to set up the transition matrix, I'm going to have this. I'm going to say, all right, probability of going 0 back to 0 is 3. Probability of going from 1 to 1 is 0.1. 2 to 2, also 0.1. 0 to 1, 0.3. All I'm doing is reading the probabilities off the arcs. From 1 to 0 is 0.4. To going from 2 to 0, 0.2. let's see, the columns should add up to 1. So we have a 0.3, a 0.3, so that going from 2 to 0 should occur with, what, 0.3 as well? And that one says 0.2. This will be 0.5, going from 1 to 5. Sorry, it's the rows that sum up to 1. So going from 1 to 2 has probably 0.5. Going from 2 to 0, probably 0.2. So this should be 0.7. Sure enough, there it is. Okay, so that's how we get from our transition diagram to our transition matrix. And likewise, we could have set this up first using this information and put it into the transition diagram. Now, it is possible to have a Markov chain where you have the current event dependent on the two previous events, but you have to set up your states accordingly. So let's go to a simpler example. Let's say that you have just two options on the weather this time. You have, or actually, let's say there's a, let's call it a readiness thing. And let's say, all right, I have an airplane, I have a C-17, and it's either operable or not. It's either flying or it's not. So let's call state 1. We're going to say that state 1 or state 0 means flying, and state 1 means it's in-op, it's not working. Okay. So we could say we may have a transition matrix that just has the probability of going from flying to not flying, and vice versa, and so forth, for one time step. But let's say we want to do this for 2 time steps. So we want to say, okay, whether it's flying today depends on whether it was flying yesterday and the day before. Now we would redefine our states, and we would potentially have, we could either do it like this, where we could stay states 0, 1, 2, 3. So state 0 would be if we had flying, we're going to say yesterday and today. So 0 is going to be if it was flying yesterday, flying today. State 1 is if it was flying yesterday, not today. This is if it was in-op yesterday, it's flying today, and then this is in-op 2 days in a row. So now we can use these states to model a Markov chain that depends on the last 2 days worth of history. But see, we've collapsed them into 3 states instead of having 2 variables here, or 2 numbers there. Now, note, if you're depending on the last 2 days, if today it is operable, the only states you can go into are 2 and 3, because if it's flying today, then we can't be in either of these states tomorrow, because these would have to be a 1. So since it's flying today, tomorrow we won't be able to say, well, yesterday it wasn't flying, because yesterday it was flying. Okay, so think that one through. But this will give you a transition probability of 0 when you start to collapse these things together. There is a homework problem that uses that principle. How many states? So in this case, we have 2 choose 0 plus 2 choose 1 plus 2 choose 2. But let's say that we want it to be dependent on the last 7 days of maintenance history. Well, that's another whole story. So if it's the last 7, now we're going to have 7 choose none of the last 7 days plus 7 choose 1 of the last 7 days plus all the way up to 7 choose 7 of the last 7 days when it was in one state or the other. And you end up with 128 possible states. So quickly that can get extremely messy. Not the easiest way to do it. So that is a summary of the beginning of Markov chains. So take a read through the homework, and then in class we'll go through an inventory example. By the way, we talked about binary probabilities in these examples, but think back to some of the stuff we did in reliability. It's possible to have a probability that is that's not binary, that follows another distribution. So take that into account, and we will talk about our inventory problem in the next class. See you then.